Welcome to this third presentation of Elements of Neural Network and Deep Learning Part 3. I am Tiniam B. Ganesh. Like my earlier two presentations, this presentation is also based on materials from two courses at Coursera, Neural Networks and Deep Learning by Professor Andrew Ng, and Neural Networks for Machine Learning by Professor Jeffrey Hinton. I've also taken material from two books, Neural Networks and Deep Learning by Michael Nielsen, and Deep Learning book by Ian Goodfellow, Yoshua Bengio, and Oren Corwell. I've also used other material from the internet. So in my last presentation, I showed how we can implement a logistic regression as a two-layer neural network with just the input and the output layer. Now we will look at the most simple of a neural network, where we have an input layer and an output layer, and in between the input and output layer we have what is known as the hidden layer. Typically a deep learning network will have more than one hidden layer. If you have just one hidden layer, it's called a normal neural network. With more than one hidden layer, it becomes a deep learning network. And these circles are activation functions. These activation functions can be any nonlinear function like a sigmoid function or a tan function or a ReLU function or a leaky ReLU. And basically these functions are what give these neural networks the power. And at the input layer, we will be providing the input features, and we will be weighting each of these features as they traverse across the neural network. So the activation functions, which were represented by circles in the earlier slide, we can have a couple of activation functions. For example, we have already seen the sigmoid function, which basically at 0 takes a value of 0.5. and values greater than 0, it increases linearly, and then kind of plateaus for larger values of z, and similarly for values less than z, it slowly decreases, and for very large negative values it goes it touches 0. The tan function also has a very similar characteristics as the sigmoid function, except that instead of being varying between 1 and 0, it varies between -1 and +1. And it has an average value of 0, so it has some good characteristics. And finally we have the ReLU function, which is known as the rectified linear unit, which has a value of 0 for all negative values, and values which are positive, it has the value of z. So it is one of two values, max of 0 or z. Typically these activation functions, whether it's tan or sigmoid or ReLU, they are non-linear. It is very essential that these activation functions in neural networks be nonlinear, because that is how we can get all the nonlinear characteristics of neural networks and deep learning networks. If we did not use these nonlinear functions and instead directly used linear functions, basically what will happen is the neural network, whenever we are trying to do a binary classification, will reduce to a basic logistic regression and will not be of any help regardless of the number of hidden layers that you tend to use. And this can be shown very easily. Hence it is necessary that the activation functions be nonlinear. However, there is a case where you may need to use linear activation functions, that is if you are trying to use a neural network for multivariate regression. Now let us take a simple three-layer neural network. We have two inputs, x1 and x2, and a bias term b1, and we have weights w11, w12 and w13 for the input x1, and w21, w22 and w23 for x2, and we have the bias term. And the superscript 1 basically essentially says that this is at the layer 1. So we can calculate this activation z11 by taking x11 into w11, x2 into w21 plus b1. Similarly, z12 is w12 x1, x2 z12 is x1 into w12, and x2 into w22 plus b1, and z13 is w13 x1, w23 x2 plus b1. And then we have on the other side we have the activation function. As I said, this activation function can be any activation function. We can use a sigmoid, we can use a ReLU, or we can use a tan. Typically sigmoids are usually used at the output layer, because sigmoid has the characteristic of 0 and 1, and if it in the intermediate layers, typically a tan H or a ReLU is typically used because you get better performance. So here in this intermediate hidden layer, I've used the tan H as the activation function. So A11 will be tan H of Z11, A12 will be tan H of Z12, and A13 will be tan H of Z13. And now we can calculate the next activation layer at the output. Z21 is equal to W11 superscript 2, because it's second layer, into A11 plus W21 superscript 2 into A12 plus W31 superscript 2 into A13 plus B2. And A21 is now at the output, since it's a binary classification, we use sigmoid of this output Z21. Now we can simplify this using the matrix notation. Now we can simply say the Z1 vector, Z1 is a vector of Z11, Z12 and Z13, and we can since this is just a matrix multiplication, we can rewrite this equation as W11, W12, W13, W21 superscript 1, W22 superscript 1, W23 superscript 1 into X1 and X2. So if you see, you'll be multiplying W11 superscript 1 into X1, W21 superscript 1 X2. So like that you will get, and you will get exactly these same three equations. Similarly, we can show at layer 1 the activation function as a vector of A11, A12 and A13, which is tan H Z1, tan H Z12 and tan H Z13. And at layer 2, similarly we can write a capital Z2 is equal to Z21 is a multiplication of W11 superscript 2, W21 superscript 2, W31 superscript 2 into Z1, Z12, Z13 plus B2. And A2 is basically A21 sigmoid of Z21. So basically this is just rewriting the same equations which we saw in this page as using a matrix notation. Now we can just simply write this as capital Z1 is equal to capital W1 into X1, X plus B1. Capital A1 is tan H Z1, where Z1 is a vector. Similarly, Z2 is capital W2, which is a vector, into A1, this activation function, plus B2. And A2 is the sigmoid of this second layer activation, Z2. Now let's look at some important results. d by dx of Ex is Ex. I mean that is obvious. And d by dx of e power minus x is minus of e power minus x. And sin hx is hyperbolic functions e power x minus e power minus x divided by 2, and cos hx is e power x plus e power minus x divided by 2. If I take the derivative of d by dx of sin hx using these two results, we can show d by dx of sin hx is equal to cos hx, and d by dx of cos hx is sin hx. And this is the familiar division rule. If I try to do d by dx of f of x divided by g of x, then it is g of x into d by dx of f of x minus f of x into d by dx of g of x divided by g of x square. And this division rule is important when we are trying to find the derivative of tan hx. The derivative of tan hx, since tan hx is equal to z is equal to sin hx divided by cos hx, we can say d by dx of tan hx is equal to this denominator cos hx into d by dx of sin hx minus cos hx into d by dx of sin hx divided by 1 minus sin hx squared. Okay, so yeah, so tan hx is equal to z equal to sin hx by cos hx. So d by dx of tan hx using the division rule is cos hx into d by dx of sin hx minus cos hx d by dx of sin hx divided by 1 minus cos hx squared. So if we take this, d by dx is equal to cos hx, if d by dx of sin hx we know as is cos hx, and d by dx of cos hx is sin hx. So using these values we get cos hx squared minus sin hx squared divided by cos hx squared, and then just reducing this equation, you find it's equal to 1 minus tan hx squared. But since tan hx is equal to z, we can now reduce this to d by dx of tan hx is equal to 1 minus tan hx squared is equal to 1 minus z squared. Now forward propagation, as I said, what does neural network do? We need to be able to, we have to see how we can reduce the cost at the output by varying the weights on the input. So we need to, and this is done by a process of gradient descent. So we will need to, for each iteration of the this gradient descent, we will do one cycle of forward propagation and one cycle of backward propagation, where we will determine the derivatives of the cost with respect to the weights, input weights, and we'll subtract this gradient from the weights, and we will then compute the cost. So we will have to repeatedly compute the cost for each forward and backward propagation, and if our learning rate is chosen appropriately, we will find that this cost tends to keep on decreasing, and we can continue this process till we get a very low cost. So first we will have to do this forward propagation. So we have the inputs capital X, which is a vector, and then we have the bias, and so this activation Z1 is equal to W1x plus B1, and then we calculate the activation function using the tan hx. A1 is equal to tan h of this Z1, and Z2 is a vector again. We take the weights in the second layer, multiply it with the activation of the first layer plus B2, and since it's a binary classification, we use the sigmoid of the activation Z2 to get the activation function at the output. So this essentially is the forward propagation cycle. So we know the inputs, we know the weights, and we go through one cycle of the forward propagation. Next we have to start with the backward propagation. So we know the loss for a binary classification. We've already seen it in presentation 2. It is minus y log of this activation A2 plus 1 minus y log of 1 minus A2. And this result we have already seen, dl by dA2, since d by dx of log x is equal to 1 by x, it can be shown as minus of y divided by A2 plus 1 minus y divided by 1 minus A2. And if A2, since A2 we are using a sigmoid function, we have already seen that dA2 by dZ2 is equal to A2 into 1 minus A2, which is, we had seen in the second presentation. If we use the sigma function for the sigmoid, then d sigma by dz is equal to sigma into 1 minus sigma. Similarly, if since z2 is equal to w2 a1 plus b2, dz2 by dw2 is equal to a1, okay, since b2 becomes a constant, and dz2 by db2 is equal to 1, and a1 is equal to tan h z1. We have already proved that dA1 by dz1 is equal to 1 minus tan h squared, which can be proven as 1 minus a1 squared, and z1 is equal to w1 x plus b1. Therefore dz1 by dw1 is equal to x, and dz1 by db1 equal to 1. So these are the results we will use in the actual backward propagation computation. So these are the more detailed derivation of the backward propagation computation. And as I said, what are we trying to do in backward propagation? We are essentially trying to find how the loss varies for the changes in weight W1, W2 and the bias. And once we know how the loss varies, we can use gradient descent, which is we can iterate W minus alpha of dwi dl by dwi, and b is equal to b minus alpha of dl by db. That is essentially what we want to do and we want to compute. So here first let us find dl by dou L by dou Z2. Using the chain rule, we have this equal to dou L by dou A2 and dou A2 by dou Z2. Now dou L by dou A2 we have already found, it's equal to minus of y divided by A2 plus 1 minus y divided by 1 minus A2, and the dou A2 by dou Z2, this is a sigmoid function. We know the derivative of sigmoid function is sigma into 1 minus sigma. So here since sigma is equal to A2, it becomes A2 into 1 minus A2, and if you multiply this will reduce to A2 minus y. Similarly, dou L by dou W2, we can use the chain rule, dou L by dou A2 by dou Z2 by dou W2. we already know that dou L by dou Z2 is equal to A2 minus Y, and all we have to find is dou Z2 by dou W2, which is nothing but A1. Similarly, dou L by dou B2 essentially reduces to dou Z2 by dou B2 and dou L by dou Z2. Dou L by dou Z2 is A2 minus Y, and dou Z2 by dou B2 is 1. So this becomes A2 minus Y. Now let us find dou L by dou Z1. Since this is the activation function, this is equal to dou L by dou A2, dou A2 by dou Z2, dou Z2 by dou A1, and dou A1 by dou Z1. So dou L by dou A2, dou Z2 is A2 minus Y, dou Z2 by dou A1 is equal to W2, and lastly we have dou A1 by dou Z1, which is the tan H. So this becomes 1 minus A square, and lastly, so this becomes 1 minus A square. This is exactly the same. So you have A2 minus Y W2 1 minus A1 square into X, and lastly if you take dou L by dou B1, it is dou L by dou A2. We start from here, dou A2 into dou Z2, dou Z2 into dou A1, dou A1 dou Z1, dou Z1 by divided by dou B1. So dou L by dou Z2 we know it's A2 minus Y, dou Z2 by dou A1, dou Z2 by dou A1 is W2, and dou Z1 by dou B1 is equal to 1 minus A square. Okay, so these are the basic things. So now we see in this backward propagation, we have essentially found the gradients. The key gradients we are interested in is dou L by dou W1 and dou L by dou B1. These are the two gradients we have to find, and once we have these two and also dou L by dou W2 and dou L by dou B2, we can compute the weights at each layer for each cycle of gradient descent. And after each cycle of gradient descent, where we change the weights and find the new loss, new cost of this change, then what we do is we keep continuing this process till our cost keeps on reducing and starts plateauing towards the bottom. At that point, we stop our iteration gradient descent and say that is our current best value. Here's a computation graph which is in this deep learning book. So as I said, this this neural network starts from here to here. You have the inputs and then the weights W1, B1. You find the Z1 activation, then you have the tan H activation function, then you have W2, B2, you have Z2, and finally the sigmoid activation and the loss. So if you take dou L by dou A2, we have seen, we know the loss equation, and if I do this, we know it is minus Y by A2 plus 1 minus Y divided by 1 minus A2, and Z2, dou A2 by dou Z2, which is sigmoid function, is A2 into 1 minus A. Now if I take this, so dou L by dou Z2, if I that is basically the product of this and this, it is A minus Y. Similarly, if I have this equation, that is dou L by dou Z2 by dou A1 is W2, and dou L by dou A1 is this. If I multiply this, I will get the dou L by dou A1. So basically we work through this computation graph. This chain rule, whatever you have seen, is basically represented in this computation graph. So here I want to show how the performance of the neural network compares with a logistic regression. So this is a non-linear 7 clusters of binary classes, and it is you cannot have a linear line, it cannot be separated by a linear curve, linear line. So if you use logistic regression, typically you will tend to get a straight line like this, which is not very good. You can see that there are some yellows here and some yellows here. It's not being a clean separation. However, I would have to admit, if you use support vector machines, you could get a much better separation. Now the same problem when I ran with my neural network, 3-layer neural network, I get a very clean separation with just a little bit of error here and there, some dots, yellow dots, but it has a very clean separation. And here is another example where you have an outer of positives and an inner negative. It very cleanly separates these two layers with a nonlinear boundary. So this can be automatically done by a neural network. The only thing is we have to make sure that we choose the correct learning rate, we choose the correct activation function, and we choose the number of hidden units. All of that, it's a bit of tuning that is required in the hyperparameters. But once we have all of this, we can it does it a very good job of this. So this concludes the third presentation of neural networks and deep learning. Thank you.